Okay, hello, good day, and welcome to my presentation. Who am I? I'm a C++ programmer. I started my career with networking protocols, and then I did quite a lot client-server programming. At some point, I started to use Qt, and that leads quite naturally to user interfaces. So my platforms are Linux, Windows, and recently embedded. I'm a freelancer, you can hire me, and I'm somehow concerned about performance. In this talk, we will start out with a short intro into the field of memory allocators. Then we will introduce SDL allocators and show how PMRs, polymorphic memory resources, improve upon them. And that will allow us to understand the two advanced techniques we will discuss in the following. We will close up with some general remarks. So memory and performance, how do they impact each other? We know allocating memory is costly and accessing memory is slow. Caches are important. Memory locality is important. We want to keep that talk on the intermediate level, so I won't explain all that, and I will just assume you know why the situation is like that with our modern hardware. As programmers, we can shield ourselves from that complexity by using system memory allocators, which are provided by the runtime of C++, but there is also a long-standing tradition of writing custom memory allocators. Why is it that? Why is it so? First of all, we can gain performance from by increasing locality of memory accesses, and we can also lower costs of allocations. For example, when we avoid locks, if we don't need to lock the allocator. Second reason is that we will be able to place our object in a special regions of memory, like shared memory, file map memory, high bandwidth memory, even on program stack. We can use it also for security, to prevent some memory related exploits like Chrome is doing, or for debugging, just printing some debugging for. So what did I know about allocators before I started to investigating this topic? My first encounter with that was when I've seen a sized block allocator used for allocating networking packets. Simple C++ new operator overloading in a class was all that was needed for that. And I heard about arenas, which I assumed would be just a buffer when where allocated objects will be placed. My second encounter was when I read about an XML parser that implementation that were using lists as internal data. We know lists aren't terribly good performance-wise because of the inherent non-locality. So the author of the parser just used a simple memory buffer-backed allocator that just pumped up a pointer when allocating a new object. So with this allocator replacement, list performance problems were solved, and that just impressed me very much, because there is this data structure which is inherently bad for performance, and nonetheless we can use it and make it work. Next, I learned that in game programming that they are using a plethora of allocators because they are constantly creating objects at runtime, like meshes, sprites, textures, and so on. The classic book here, Game Engine Architecture, mentions 5 types of allocators: stacked allocators, pool allocators, aligned allocators, single frame allocators. So, and an example game, Jack and Dexter, keeps all the time 3 memory allocators, and 2 of them are have loaded all the data which are needed for the current game level and for the next game level, so that we can seamlessly change from one game level to another. So what is the situation in C++? We have STL allocators. In a standard template library, an allocator is a template parameter for a container. Originally, the allocators were meant to encapsulate different pointer sizes on some ancient PCs. That's all in the past. Currently, they evolved to be just a general memory allocation service for containers, and they constitute one of building blocks of standard template library. However, the allocators, as they were designed or defined at that time, were rather problematic to use. The original design was technically lacking in several aspects because of time pressure. They didn't want to compromise the deadline. Okay, we've all been there, so no hard feelings in that respect. Second problem was they were hard to use because as allocator is a part of the container type, a vector of integers using 2 vectors of integers using different allocators don't have the same type and can't be used with a general function like a function we've defined here, taking just a vector. So no, there is no surprise that the allocators as defined then were little loved and little used. But fortunately, there was that company called Bloomberg, and they have developed their own allocator library before STL came up. And after that, they tried to merge both worlds, and finally they joined also the committee to work on allocators. So it's their work, basically. The idea was to wrap the base class for allocators in an STL conformant allocator wrapper, and then always use the wrapper in the signatures on STL containers, so all the containers will have the same signature. The second idea was to add allocator as parameter in constructor for classes, so that it could be passed down the chain in the container to the contained objects. In C++ 11, we've got this design partly implemented, so the technical issues were solved, but allocators were still part of signature of containers. Again, no time, and this was postponed to C++ 17. So in C++ 17, a new namespace was introduced, PMR, and all the almost all the classes, Bloomberg classes, were ported to that namespace. What is PMR? What does it mean? Some people told me it stands for poor man's Rust. Well, maybe. And other people tell me it's acronym for polymorphic memory resource. Not much better. But wait. Shouldn't it be polymorphic memory allocator and not resource? What is that resource thing? Well, the explanation is that the polymorphic allocator name was already taken, and it is the name of the general wrapper which we plug into the standard containers, standard container template definition, and it holds a pointer to an abstract base class of the object doing real allocation work, but they have had to call it something else, and well, it was called memory resource and not memory base allocator something. Well, it's somehow confusing, but we have to get used to it. And well, let's have a look on allocators. Allocators, I'm still mixing up these two names, allocators and memory resources. So what memory resources are provided to us by standard template library? Basically, you have two types of resources, monotonic buffer resource and the pool resource, where the pool resource can be synchronized and unsynchronized. This means with internal locking and without. Monotonic buffer resource will use a backing buffer. Memory buffer to place the allocated objects within, and it will only release the allocated memory when the entire resource is destroyed. So it's a kind of pointer bump up allocator we've seen before. We discussed at the begin of the presentation. So why the name monotonic? Because in mathematics, if a function is always growing, it's called monotonic, and this memory resource is good for data structures that are built up only once and then just used and discarded. Pool resource is somehow different, and it is optimized for allocating blocks of single sizes. And the pool allocator keeps a collection of pools which serve requests for different block sizes each. This allocator is good for data structures with numerous insertions and deletions because of memory reuse. That means if we are releasing memory for some object, it will be returned to the list of free memory in the pool and then reused later. And as we will see later, because of it provides quite good memory locality. So, show me the code. Here it is. Here we first defined a buffer which will be used to allocate objects inside of it, and then we passed this buffer to a monotonic buffer resource. This is that pointer bumping up, pointer bump up allocator, so to say, and this monotonic buffer resource can be passed to our containers, to the standard containers in constructor. And one thing to note here is that we are not just using standard vector but instead standard PMR vector, which has built-in support for forwarding of the memory resource and its allocator down to the contained objects. We can reuse this memory resource by calling its release method. It will rewind all the resource to the beginning, and we can start allocating with a fresh slate. Pool resource looks somehow different. It has several pools of which cater for different allocation sizes, and each pool manages a collection of chunks that are divided in blocks of this uniform size. If a chunk will get exhausted, next chunk will be fetched from the upstream allocator. So what is an upstream allocator or an upstream, better an upstream resource? Well, it is it is a fallback resource. If a memory resource exhausts sorry, it's the memory it owns, it can get additional memory from that upstream allocator. The default upstream allocator, when we don't set another special one, is our good and trusty new delete resource with that will just call new or delete operators, global new or delete operators. We can also set the default resource for our default memory resource for our program. And why should we do it? Well, basically for testing and debugging, we can set a default memory resource for in a use case, in a unit test, and get our debug information. So that closes the short introduction of PMRs. Are there any questions at this point? No. Okay. So yes.
There's only one question, not really regarding this, but on slide 10, what are the lacking features in the STL allocator?
Lacking features. Oh, it's a very, very big topic. So I didn't include it here. Okay, so standard allocator instances were defined stateless, so they are always compare equal. So we, as originally defined, we couldn't program a stateful allocator. Then pointer types were just short circuited to the type to the pointer to the type. So no fancy pointers, no special pointers were allowed. And then were the problems. There were also problems with forwarding the allocators of the containers to the elements it contained. It wasn't well defined. So this is the part of the standard that messes with this all up. And yeah, this is a little more explanation, but I just wanted to skip it. It is a very big topic. Sorry. Okay. So,
Marek, do you have time for another question? Here's one question. Stood PMR vector API. Is it compatible to STD vector? Stood vector?
PMR. Let me see. Okay, I have to skip to my sort it out.
Yeah, it's on slide
materials 8. To find it. Let me see, where is it? Oh, can't find it. No. Yes, yeah. PMR vector just uses this yesterday PMR polymorphic allocator as part of its type signature. So we don't have to do it for ourselves. And it also provides some support for allocator aware classes. We will discuss this later. But the basic feature is that it's simple type def, where we just fix this allocator to the base of allocators of the polymorphic allocators.
Yeah, so I think we have the chance for more questions on the Q&A table in the line.
It's a big topic, so one could make a talk entirely from these definitions of allocators and of allocators APIs, and so I wanted to skip it.
Okay, so yeah, go on with the
because we want to have a look of some of the more advanced techniques. Well, okay, the first technique is called Wingout. So the monotonic buffer resource has a method called deallocate, which frees the memory, and it's no operation. It is doing nothing. Interesting. Well, it has it follows that the destructor for the element is not called. Yay, time savings. Time savings, we are increasing our performance, but we have another problem. When we have a container which contains elements allocated from this monotonic buffer resource, containers destructor will be still called, and container destructor will call the destructors of the elements, so we've gained nothing. But there's a trick. We'll just use monotonic buffer allocator for the container also, and we in this way we never invoke the destructor of the container, and the destructor of the container will never invoke destructors of the contained objects. So it all just disappears without cost. And the allocator just bumps down pointer to the beginning of the buffer. So it's like magic. Of course, caution. It's not without reason that it's somehow advanced technique, because no side effects are allowed in destructors, because destructors won't be called. And if we are freeing some other resources other than memory, well, then we have a resource leak. Another problem with that is that we have to take care that the container doesn't contain any objects that were allocated using a different monotonic buffer resource object. So we have always to be very cautious with this technique. So you probably didn't understand anything. So let us have a look at a code example. So we define, for example, an unsynchronized pool resource, because the destructor of pool resource also does nothing. And then we defined a polymorphic allocator using this pool resource. Okay, and then we just construct a vector of list of strings using our pool allocator. So can you see? It's just a pointer. We don't hold to the pointer. And is it a memory leak? Maybe. It could be. Okay, and then we use the data, push something and push something and push something again. And then we are out of the scope. So normally this should be a memory leak, because this pointer won't get freed. We don't call delete for that. We don't call delete objects on the pool resource. It just goes out of scope. But as it goes out of scope, this unsynchronized resource will call its release method in the destructor, and everything just wings out without any destructors, and the allocation is almost free. So there's a quote. It's just a very cool technique. When I was writing the example code, I encountered a couple of problems. First, I tried to, naive as I was, to do it in the old Bloomberg style, just to forward a pool resource or pool allocator to the new constructor, because Bloomberg conveniently has overridden the global new operator to use the allocators. Well, this didn't work, because it just crashed, because in C++17 there is no such overload, unfortunately. So I have to look in the standard to figure out how to create a new object using a given allocator instance, polymorphic allocator instance. In C++20, there is this very convenient method known as new object, where we just have to templatize it on the container type we want to create and everything. And it is done in one line of code. In C++17, it's more complicated, because, well, it's a two steps process. First, we have to allocate memory to contain the new object to be created, and then we have to construct this object in this memory. So, well, it's not very good support for the programmer. It's very low level, and also I have a big problem, which I initially didn't understand, with this pull resource forwarding. Should I forward this pull resource to the constructor of vector of list of strings so that it will use it for its internals? Well, I just always got pages of some template errors which I didn't understand, and I had to look at the implementation, at the code, and well, the reason was that at this point we don't need we can't use the resource because polymorphic allocator construct shouldn't pass resource down the chain. Well, okay. So with this, the problem was fixed, but I didn't understand it. We will come to that later. So, but first, let us think about undefined behavior. Well, this all is much too good to be true, isn't it? You just don't run any constructors, you just ignore objects which are were constructed, and is it allowed? Is it kosher, or is it undefined behavior? For that we have to consult the ultimate oracle, the C++ standard, and in the section basic.live 0.5 it says that a program might end the lifetime of any object by just reusing the storage. And the second possibility, by calling a distractor. And moreover, program is not required to call the distractor explicitly. This tells us that Wingout is basically safe up to a point, because any program that depends on the side effects produced by the distractor has undefined behavior. So there is that gotcha again. We can't have any side effects other than freeing memory in such omitted distractor. Okay. Now I provided to you an excerpt from real code base. It's C++ actor framework, CAF, and here we have part of implementation of JSON data representations, JSON representation data structure. So now that we learned about wing-in and monotonic and buffer and resources, we can understand what the code, this command says. And it says this JSON abstraction is designed to allocate its entire states in a monotonic buffer resource. Okay, it's clear now, isn't it? And this minimizes memory allocations, because we have just a simple bump up, a pointer bump up for allocations, and also enable us to wink out the entire JSON object. We know now what wink out is. Yes, I think so. Entire JSON object by simply reclaiming the memory without having to call a single distractor, and that is clear also. The API is not optimized for convenience or safety. The key word here is safety, because, well, there is undefined behavior lurking. If we have some side effects, it's not safe. Since the only place we use this API is JSON Reader, but it's okay because they are using it internally. Okay. Another example where this Wingout trick is used are protocol buffers. Google protocol buffers. They are it's a framework for serializing and deserializing data structures. And for in C++, the backend, we can enable an arena allocator, which uses a large piece of pre-allocated memory called arena, of course, and we can wink out the whole serialized data structure when the arena gets destroyed or goes out of scope, just like we were doing in our monotonic data resource example. However, string fields are not allocated on the heap allocated on the heap and not on the arena. I don't know why. I never found an explanation for that. So there is one feature which STL doesn't provide. We can register distractors to be run on destroying when the arena gets destroyed for external objects, if they're depending on some internal arena objects, but also for internal objects, if should they have some side effects and should they require the destructors to be run. And we can reset the arena to its original state, just as we did it with monotonic buffer resource. Well, the second advanced technique we want to discuss is called localized garbage collection. So we know that large graphs created with shared pointers have been known to overflow the stack on destruction. That's because each node's destructor will recursively call the destructor for the next node in the graph, and that can result in unbounded recursion and a crash and stack overflow. Even worse, the problems are even more tragic if there may also be cycles in graphs. So what is our idea to solve this problem? Well, we just use our previous technique and wink out the entire graph at once, not calling any destructors, avoiding stack overflows and deep recursions, and well, very elegant solution. We don't need any language extensions, any new smart pointers. And the code, you can see the code here. We have we have graph nodes, we have outgoing edges and payload. And first we allocate the buffer to be used for the monotonic buffer resource, and then we give it to the allocator called buff_alloc in this example, and then we allocate new graph nodes, connect them, and just play with them. Okay, and on the end, at the end of the scope, of course, buffer, allocator, and his memory resource will be reclaimed. and none of the destructors will be called, and everything will be winked out, just like that. Problem solved. We have to notice that we aren't using smart pointers here. We are using naked pointers. Okay, and when creating objects for the localized garbage collection example, I encountered the same problems as with this first Wingout example, where I allocated a vector list of strings. So naive mode crashes, C++17. In C++17, we need a two-stage allocation and construction, and in C++20, we just use our new object method, convenience method of the allocator. The difference here is that GraphNode somehow needed the memory resource to be passed in this called new object, and that is very different from the previous example where this wasn't allowed. I tried to solve this conundrum, and the reason is that allocator, that this GraphNode is not defined as an allocator-aware class. What is an allocator-aware class? Okay, it's complicated, but we can make a GraphNode allocator-aware by type defing this allocator type to be polymorphic allocator, and then, well, look here, the last line of the example. With that, the allocator don't have to be passed down. The buffer allocator will pass down himself to the GraphNode. So this is this was a localized garbage collection, and it essentially is a Wingout with naked pointers, but a very, very elegant solution of a pesky problem. And we have the same caveats as with Wingout. And another problem: why aren't we using? We are using naked pointers, and it shouldn't be the case in modern C++. Well, can we use smart pointers after all? Well, not really, because they don't really mix well with polymorphic memory resources. One of the creators designers of PMRs, John Lakers, said that certain standard facilities like shared pointer that manage object lifetimes don't mix well with memory resources, because they neither track nor extend allocator lifetimes. They are just independent mechanisms. And well, this is a big caveat at this point. So but PMRs, smart pointers support polymorphic memory resources. Well, yes and no. We can we can pass an allocator in constructor of shared pointers to just and it will be used to allocate its shared memory pointer, shared pointer internals. we can also create a complete shared pointer using PMR, which will use a memory resource with this new allocate shared factory method. And in this case, shared pointer will use our allocator for its internals, for its managed objects, and it will also pass the allocator down to sub-objects of its managed object. Well, however, shared pointer itself, it's not allocator aware. It doesn't have extended copy move constructors like normal allocator aware classes have, nor has it a get allocator method. And this, what does it mean? It means that the container of smart pointers won't forward and its allocator to the elements. Well, it's an anticlimax somehow. Well, there is a recent extension, a new feature in C++ 20 distractors, when we can tag a distractor with standard destroying delete type, and this means that a distractor that delete expressions won't execute the distractor, and in this way we can just disable some distractors to be called. And I even tried to come up, and I even came up with a scheme of using this feature with shared pointer in a graph that could work, but I'm not really sure if it's defined or not, well defined or not. It's complicated. So, summing up, allocators are difficult to write. So, but every developer can just use the allocators provided to us by the standard template library. Second point is allocators are not only for performance, therefore there are they can also do a lot of other things we discussed. Are there any costs involved? Yes, of course. We have to learn about these classes. The containers will be harder to test. Winking out is inherently from experts only, says John Lakers. And there are a couple of gotchas, like container shouldn't outlive its allocator, that shared pointer are not allocation aware, and so on. Can we do better? Well, we removed the type dependency from on allocator using PMRs, but we have still problems. Allocator aware classes require non-trivial structures. Compiler generated copy operations won't work with them, and move operations also. So it would be very convenient if we could push all that hard work down to the compiler, and indeed there will be maybe, well, indeed or maybe, there is a language proposal on the way where we can just write, okay, I have this hash map from string to list of something, and I just want to use this allocator for that, and compiler will do what is needed to make it happen. So thank you for your time and for your attention. And are there any questions at this point?
Yeah, so thank you, Marek. And actually, there's nothing on the Q&A board. So any questions anyhow?
Cool. Then everything was clear. Very well. I like it.
Yeah. So else, everybody is invited for the Q&A table and the launch. So Marek and me, we will stay there for your questions. And Marek, wait for your questions there.